So I think we're going to start. Thank you very much, everyone, for coming to our tech talk today. And I am really excited because we have a great treat today. We have Momita Bhattacharya, who has been working with us for the last 3 years, maybe, on one of our projects. And she's going to give us to talk about her results. And she's been working mostly on electronic health records. So that's really something we are very interested in. So Momita she's very young, but she has an extraordinary resume. She is right now a graduate student in the computer science, a PhD student, the computer science department at University of Delaware in the biomedicine and machine learning lab. She has published quite a lot in these last few years, and her last paper has been, she was invited to write for the IBM program. And it was one of the 10 papers to be included into the special issue of the Journal of the GMT, Medical Informatics and Decision Making. So really very impressive. She's had multiple awards. Last one in January 2018, the Aldebaran Laureate Forum finalist. And it's I didn't know about it, but it's a very famous forum where some of the most prestigious prizes in mathematics and computer science meet with 200 outstanding young researchers from all around the world. And last year in the summer, she went to do an internship at the Pacific Northwest National Lab to develop conditional logistic regression using penalty to identify biomarkers for type 1 diabetes. And in the past, which I didn't know, she was a software developer for Bank of America and Merrill Lynch. So this is really fantastic. And I'm so grateful that you are here, and we can't wait to hear you. Thank you very much.
Hi, everybody. Thank you, Dr. Jerkovitz, so much for the lovely introduction. All right, so I'm Momita Bhattacharya, and I'm in my 5th year of PhD candidate. And yeah, Dr. Jerkovitz has already mentioned that I'm working in computational biomedicine and machine learning lab. Can everybody hear me okay?
I can't hear you too well. I'm listening to a lot of
stuff. Okay. This is working? Yeah, is this better? All right. And today I'm going to talk about some of the work I've been doing in collaboration with Dr. Jerkovitz and Christiana in specifically applying machine learning for disease prediction and patient risk stratification in the context of chronic kidney disease. All right. So my plan is to talk about 3 different topics or projects. The first is identification of patterns of co-occurring medical conditions among kidney patients. The second is applying machine learning stratification of patients into their CKD severity levels, automatically stratifying patients into their CKD severity levels based on simple non-text information gathered from office visit records. And finally, I'm going to talk about a little bit about an ongoing work of prediction of hospitalization from among kidney patients. All right. First, let's talk about identification of patterns of co-occurring medical conditions among kidney patients. So the data set, as I'm sure you know, that the EHR data that we are working from, that we obtained from Christiana, is a large electronic health records a data set consisting of more than 10,000 patient records, and it has 3 different record sets: office visit records, which includes diagnosis, condition, medications, vital signs, demographics. There are lab test results, which includes various lab test measurements, and hospitalization records, which has information such as length of stay, type of visit, etc. And all these individual record sets are longitudinal, and they're extremely heterogeneous. They offer a plethora of challenges, like missing data, imbalance data, and varying time point visits of different patients. For the first part, where I'm going to talk about identifying comorbidity or co-occurring medical conditions, we are just going to focus on medication, diagnosed conditions among office visit records and hospitalization records. All right. So just to motivate this problem a little bit, I'm sure this is not the forum to motivate a medical problem, but I would do it anyways. So let's say there is this patient who has these 4 conditions: hypertension, hyperlipidemia, diabetes, proteinuria. There's another patient who has these 4 conditions. Then we have 2 more patients with 4 and 5 conditions diagnosed. As we can see, patient 1, 2, and 3 have all diabetes and proteinuria. Patient 1 and 3 has hypertension in addition to diabetes and proteinuria. Similarly, patient 4, 1 and 3 has hypertension and diabetes. So this is just 4 patients, but we can have thousands and thousands. In our data set, we have 10,000 patients. We want to be able to automatically identify these patterns of co-occurring conditions from the data, and for twofold reasons. One, for identifying if there is some indirect association that is not already known, and also to use this model as a recommendation. Like if a patient comes with XYZ condition, does our model say that condition A and B is highly likely? So we want to be able to capture this information from the data without any human supervision. So how did we go about this problem? So first, let me show how we transfer the electronic health records SNOMED codes to a data matrix, which can be utilized for a model. So here we are seeing, for example, so the first row is patient information for a patient with a hypothetical patient ID 1. This patient has been diagnosed 10 times by hypertension, hyperlipidemia 10 times, diabetes, and has never been diagnosed with GERD or obesity. When I'm saying 10 times been diagnosed, as in their electronic health records, since it's longitudinal data, 10 times hypertension has been, the patient has been associated with hypertension. Similarly, patient 2 has these conditions and these 5 times diagnosed with hypertension, hyperlipidemia, and never been diagnosed with obesity, and so on. Now, if you think of each of these patient records as documents, and each of these conditions, which were represented or denoted by SNOMED codes in our EHR as words, then we can think of our entire EHR as a corpus, as multiple documents, which are documents corresponds to patients, and the conditions corresponds to words. And what these frequencies show is number of times this word has occurred in this document. So now we can apply some NLP, natural language processing, or text mining analysis to identify which are the group of conditions that seem to co-occur in this patient population. For that, we used something called a topic modeling, which is a model to automatically capture topics or themes from documents. And we apply it for in the EHR. Specific type of topic modeling that we apply is called latent Dirichlet allocation, which is a probabilistic generative model. And it's based on the idea that documents can be modeled as a mixture of latent topics or hidden topics or groups, simplistically, where each topic is a distribution of words. In our case, each topic would be a distribution of SNOMED codes. And what it captures is which are the codes or which are the conditions that frequently co-occur in the entire population, and it's going to do all that automatically without any human intervention. Am I going too fast, or is it okay? Good? Okay. All right. So now let's talk about the generative process. We have a multinomial distribution over codes. In text, it's words, the words are multinomial, and in our case, the codes are also multinomial. We have a number associated with each code, 4, 5, 3. A multinomial distribution of codes for a topic is obtained by sampling from a Dirichlet distribution. We use Dirichlet because it's a conjugate prior of multinomial distribution. We then obtain a multinomial distribution over topics by sampling from another Dirichlet distribution for each patient file. And then for each code position in the patient file, we draw by sampling from the multinomial distribution over k topics, and then a code is drawn by sampling from the topic code distribution. So this is the overall generative process for latent Dirichlet allocation. We have just applied it or adapted it in the context of it. Here I'm showing the plate notation for the probabilistic topic models, where the k value represents the number of topics which we have to provide. It's a hyperparameter that we provide to the model before training the model. That is the number of topics we want. For our experiment, we run for different values of K and then evaluate which topics look more clinically relevant. P is the number of patient file. In our case, is around 13,000 patients. And N is the number of SNOMED codes. That is the vocabulary of our in our data. So what are the experiments we conducted here? We first obtained topics using Latin distribution. As I mentioned, we ranged the number of topics from 5 to 100. We ran multiple experiments for different values of K. Then we determined the best value of K using log likelihood. Wherever the log likelihood value was highest, we obtained that as a best value of K. The main challenge with any unsupervised, this is unsupervised learning approach, and the main challenge with any unsupervised machine learning method is how do we evaluate it? When there is a label, when there is a tag in supervised learning, it's easier to evaluate because then we can see how many instances did our model get correct. But in unsupervised, we have to develop our own approach to assess the performance of our model. And specifically in clinical context, we have to do two types of evaluation. One is quantitative and the other is qualitative. Clinically, we also have to evaluate if the results make sense. So we evaluate the clinical relevance of the topics by going and looking for papers which has indicated the correlations or the association that we identify by our topics. And also, luckily, we have a nephrologist in our team who has seen the topics. And then we evaluate quantitatively by assessing the tightness and distinctiveness of the topic. We do not want our topics to have all conditions with equal likelihood. Then it's almost like uniform distribution, which is not good, which is not informative. Also, we do not want all codes to have high probability across all topics. If you think about it, the conditions among kidney patients that are most likely to occur all the time, for example, hypertension or hyperlipidemia, like the very frequent conditions among, I hope I'm right with these terms, but these conditions are highly frequent among kidney patients. If those conditions kept occurring in each topic, then basically our topic is telling us nothing new. However, that was not the case, as you will be able to see by the few examples of the topics. Here I'm showing 3 topics obtained from office visit records and only a few terms. I'm showing 8 terms due to limited space. So this is a topic which seems to capture a lot of diabetes related conditions. So there is type 2 diabetes, hyperlipidemia, proteinuria, morbid obesity, neurologic disorder associated with type 2 diabetes, and essential hypertension. Then there is this topic which seems to capture pain, joint and limb pain, chronic renal failure, which has been established to have association with pain in the limb and joint pain. Similarly, there's another topic which is more chronic conditions, asthma, cough, bronchitis, disorder of lungs. You can, after the talk, you can let me know if these topics make sense, or we did best we could to find out clinical relevance of these topics. But yeah, your input will be helpful too. Also, we applied the same experiments, same model on hospitalization records. And here I'm showing example of 3 topics that were obtained from hospitalization, the SNOMED codes that were associated with patients who were hospitalized. The distribution of codes in topics that were obtained from office visit records and versus that was obtained from hospitalization records was very different. As we can see for the first topic that was obtained from hospitalization, it seems like it's heart-related, congestive heart failure, cardiomyopathy, ICD, and pulmonary heart disease. So this would be more of a heart-related topic. The next one looks more related to lungs, tobacco use, chronic obstructive lung disease, pneumonia, then obstructive airway disease, and so on. I'll hold this slide for a few seconds for you to see the topics. And then finally, this is another topic obtained from hospitalization. So what we achieved using this approach is we were able to identify these hidden latent patterns of association among patients associated with different record sets, and identify these meaningful group of conditions that might enable physicians to identify these co-occurring conditions, and also enable us to use these models in a later time for recommendation systems in EHRs or similar applications where we want to identify provide some risk of condition given a patient has a certain number of conditions. All right, and for quantitative evaluation of the topics, we assess the tightness, that is whether each topic can be specified by a small number of coded conditions. For that, we used a probability threshold. Just to remind, a topic is nothing but a probability distribution over SNOMED code. So each code in a topic has certain probability of a topic, but every topic has all the codes associated with it. It's only that some topic has some conditions that with high probability versus rest of the conditions have very low probability. So we find that by setting a threshold of 0.01, around 10 to 12 coded conditions were associated with high probability of topics obtained from office visit, and around 15 conditions were associated with topics obtained from hospitalization. That's pretty tight. So for office visit, 10 or fewer codes have probability above this threshold of 0.01. I didn't include the hospitalization record here, but for hospitalization, it was around 12 to 15. And for distinctiveness, we use a measure called Jensen-Sherr divergence, which is a improvement over KL divergence. And it basically is a measure to assess how similar or distinct two probability distributions are. And we obtained very high Jensen-Sherr divergence between topics, indicating that the topics were pretty distinct or different from one another. Example of tightness here is, I'm showing an example of tightness of topics. The x-axis here shows coded conditions. All the coded conditions are actually present in the x-axis. However, I'm showing numbers for only the ones that have significant probability of occurrence, because of which they have these peaks. The y-axis shows the probability of the coded condition given the topic. So these are a few conditions that had high significant probability in this topic. As we can see, all the other top coded conditions had very insignificant probabilities, so they were not even visible in this distribution. All right, so what are the key findings from this study? Conditions grouped together as topics by our method, Latin-Dash allocation, are indeed known to co-occur in medical literature. At least that's the assessment that we did. And we also quantitatively evaluate the topics and identify that the topics obtained were tight and distinct. All right, now moving on to our next topic. Stratification of CKD patients into severity stages based on information gathered from non-text office visit records. So the chronic kidney disease dataset consists of, this was a dataset that, this version of the dataset consists of more than 10,000, around 13,000 patient records. We use 495 simple non-text quantitative attributes present in the office visit records, including demographics, vital signs, medications, diagnosed conditions. However, once from a machine learning point of view, this could be a very simple problem where we want to use supervised machine learning methods and identify labels. However, one major challenge in biomedical data, as was in our data set, was high imbalance. That is, our data set consists of 81,000, more than 81,000 CKD stage 3 patients versus 7,000 something CKD stage 4 and 3,000 CKD stage 5. As we can see, the ratio between stage 3, 4, and 5 is 23:2:1. Using any off-the-shelf classifier was just unable to identify any stage 4 and 5 records. It was training itself to learn only stage 3 and showing really high accuracy because stage 3 just dominates stage 4 and 5 records.
So these numbers are records, right?
Records, yeah, these are records. And for this purpose, we removed the missing data records. Thus, we lost like 1,300 records. Yeah, so these are records. So we had to, because the off-the-shelf classifiers did not work, developed our own approach to address imbalance while doing it. Before going into the model, I would like to point out that we did training on past information. That is, we use records available from 2007 to 2000 as training set, and all the records available in 2015 was used as test set. I wanted to point this out because we have to keep in mind that for medical data, where we are trying to predict something about a patient, temporally early records should be used for training, which is in reality will have only temporally early records, and the later records should be used for testing. Hence, we cannot use cross-validation here. We just had to repeat these experiments by shuffling the data. All right. So this is the framework that we use for assessing CKD. We first pre-process the data to remove any variables that are known to be directly correlated to the outcome, which in our case is chronic kidney disease. That is, we removed any condition that had the word renal failure, and anything that had the word kidney also among the coded conditions. We then use feature selection. We use a method called least absolute shrinkage and selection operator, that is LASSO, for feature selection. We then conduct supervised machine learning method first by using simple classifiers like logistic regression, naive Bayes, decision tree, random forest. However, we have this devil, imbalance data, and all these classifiers fail. So we developed our own approach to address imbalance while classifying. And as always, we evaluated our model clinically as well as quantitatively to evaluate the performance of our model. All right. So highly imbalanced data set, how do we do it? We use something, as I mentioned, we first use simple classifiers. They did not work. We then use existing approaches for addressing data imbalance. For example, random undersampling. That is, there is a majority class, let's randomly undersample the majority class and make it equal to the minority class. But that way we lose a lot of information. We lose, in our case, we lose 23%, actually almost like 80% of the data because the ratio is 23:1. Then oversampling using SMOTE. Oversampling introduces synthetic instances to the data set. That usually very high oversampling can lead to moving the feature space to not replicate the original data set. What we use is improvement over meta-classification. We call it hierarchical meta-classification. We use two certain hierarchical meta-classification step consists of two approaches. The first is we first separate stage 3 records from combined stage 4 and 5 records using meta-classification. We then separate combined stage 4 and 5 into individual classes. I'll go into more details of this method in the next couple of slides. So first, let me show the data partitioning scheme of meta-classification. We have I think I forgot to mention that we only separate stage 3 from stage 3, 4, and 5 records. We did not use stage 1 and 2 information from the data set because there was some, they were not very well labeled. There are some difficulties in the data set to use stage 1 and 2. However, I've been able to improve the model now to include those records, which I have not shown in the presentation. Okay, going back to how do we partition the data? We have stage 3 records, which is now, and we have stage 4 and 5 records. We combine stage 4 and 5 records, and giving us a ratio of 7:1. What we do is now the stage 3 records, which is the overrepresented class, we divide the data randomly without replacement into 7 parts. So we are just chopping the data into 7 parts, the majority class data. We then use the complete stage 4 and 5 information and obtain 7 balanced training set. So the main challenge with imbalanced data set is we do not have balanced training set, right? So the classifier just ends up learning the majority class. So this meta-classification is a way which has not been used very frequently for imbalanced data set earlier. Gives us a way to address the issue of imbalance by producing a balanced training set without losing any data or without introducing artificial simulated examples in the data set. Now we use, now I'm explaining our model. So we have those 7 balanced training set. We train 7 base classifiers on the individual training sets, balanced training sets. Each one of them had the same feature vector, feature representation. Each of these base classifiers then predict stage 3 or stage 4 and 5. We then use these predicted outcomes from the base classifiers as the feature space. That is, we re-represent our data from its original feature space of 495 clinical variables to the predicted outcomes from these base classifiers. And then we train another layer of classifier called meta classifier to obtain the final outcome, that is stage 3 and stage 4 and 5. So we call this step in the model post classification. Then we train another simple classifier, random forest classifier, on the original training set stage 4 and 5 records to finally separate stage 4 from stage 5. And we call this stage a refinement step. So in the coarse classification step, we obtain our final prediction for stage 3, and in the refinement stage, we obtain our final prediction of stage 4 and 5. Doing all this while addressing the challenge of imbalance. So what were the experiments we conducted? We trained and tested our classifier using all the 490 features. We then used the selected features from Lasso and repeated our experiments to see if the identified lesser number of features are equally predictive of CKD stages or not. We then trained and tested our classifier using these 119 features. We also did a stability analysis on our data set. We reduced, if you remember, we have information from 2007 to 2014 in our training set. We progressively removed earlier records, that is one at a time. I think I'm showing it here. Yeah, I'll go back to the brief. So we progressively remove records one at a time, 1 year at a time. So initially we used 2007 to 14 records as training set and used 2015 records as test. We then removed 2008 to 2014. So removed 2007 records and then trained our model similarly 2009 to 14, and still we just have 2014 as training and 2015 as training. And we show we see that our results remain pretty stable. The reason is even if you look at just 2014, there is enough records for the model to train itself. At the same time, the ratio of distribution between stage 3, 4, and 5 remains consistently similar. That is 23:2:1 over the period of time. And hence, our model, this shows that our model is quite stable even in the face of much less data, which probably could be realistic in cases where we don't have so much information available for 7 to 8 years. We can have information for 2 years and would want to predict these severity outcomes from much smaller data set. Going back to my previous slide. So I wanted to show a few variables that were identified as very predictive of CKD severity levels. Some of the demographic, vitals, medications, and conditions. There's just a few examples, I think 13 or 14 variables. So for example, among vitals, BMI, systolic diastolic blood pressure, demographic, age, gender, race. For conditions, congestive heart failure, type 2 diabetes mellitus, anemia, and so on and so forth. All right. So here's, I'm showing some results. We compared the performance of our model with baseline models and simple meta classification and other approaches used for addressing imbalance data. And we see that this is our model where we are using hierarchical meta classification in the context of random forest classifier. We see that the specificity, sensitivity, and F measure all are the highest, although the baseline classifier seemed to perform, the baseline simple random forest classifier seemed to perform very well, equally well with respect to sensitivity and F measure. The reason being there is a high imbalance, and these results are average results of the 3 classes, stage 3 and 4. When we look at core class classification, we can see for stage 4 and 5, the black is our model and the gray is a baseline. For stage 4 and 5, our model significantly outperforms with respect to sensitivity and F measure compared to the baseline classifier, which is much less. As we can see for stage 3, it's almost equal or better compared to our model. But here, black represents our model, and for stage 4 and stage 5, with respect to sensitivity, it's much larger, right? The number is much higher than gray, indicating that what we really care about in medical context specifically is to be able to identify the highest risk patient, who are usually much underrepresented compared to the healthier patient. And most traditionally, off-the-shelf classifiers would not be able to identify those high-risk patients who are much underrepresented in the data set. So we need to take some approach or steps to be able to build our model so that the high-risk patients, the underrepresented patients, the minority class patients or individuals are identified with higher accuracy, in this case, higher sensitivity and accuracy. So what are the key findings of the study? We show that we are able to effectively stratify CKD severity level stage 3, 4, and 5 in the face of imbalanced data. We use simple, readily available office visit records, including medications and diagnosed conditions. And then we also show that we significantly outperform the baseline off-the-shelf classifiers and existing approaches for addressing imbalance, like simple random undersampling, random oversampling. And we retain our performance on reduced feature set as well as reduced training data. All right, so that's it for this project. Now I'm going to talk about the last topic. Which time? Oh, okay, a lot of time. Yeah.
What's the sensitivity of the model? Had somebody with 10 visits that had hypertension versus 20 visits. What was the sensitivity to having more or less that particular feature showing in practice?
So I did not conduct that sensitivity analysis. Are you talking about the CKD prediction or the co-occurrence, topic or co-occurrence? Like for the CKD prediction you're asking?
Right, I'm just looking
in
at,
general,
you know,
yeah, that's a very good point.
Well
yeah,
at 2 visits of hypertension versus somebody that's followed for 5 years.
Right.
You're going to have a large attention since you're collecting all those documents.
Yeah.
You know, how much is the model sensitive to that imbalance?
So for the topic model, yes, we did want to take into account that if there is more number of times, if a patient has been diagnosed more number of times with hypertension versus one patient who came just once and has been diagnosed with hypertension, we choose to ignore this information because we wanted to identify these groups overall in the population, not patient level, right? Like for the topics that we obtained was captured from the entire population. But for CKD, that would be addressed because we are not doing the temporal analysis. We are taking each record at a time. So each data point represents one patient visit. So one patient visit will have only one, the patient will be either diagnosed or not diagnosed.
It doesn't seem very nice model it just doesn't have look at
right. Right. Yeah. I mean, that's using the longitudinal information is the last part of the project where we are trying to build a temporal model, but the goal is then to predict hospitalization. But for the CKD part, yeah, that's a very good point. I mean, we are still working on writing the journal paper, so maybe I'll include that in the sensitivity analysis. Any other questions? So for the prediction of hospitalization event, this is very much a work in progress, but I just wanted to show a little bit of the directions we have been taking and what we are thinking about, although the model is in no way ready, and I'm not presenting the temporal model here. So what is the approach that we took for predicting hospitalization events? First, we took a non-temporal approach where we did feature selection to identify which are the variables that are highly correlated with hospitalization. We did find that the variables that we found correlated with hospitalization were not the variables that we found correlated to CKD. We then used supervised machine learning method to, by representing our data on the selected features, to see if the variables identified as predictive has enough information to separate patients associated with hospitalization and who have not been hospitalized in a non-temporal manner. We then use unsupervised machine learning method using those feature sets to, in an unsupervised manner, to learn if there is any groups of population with similar record values that are directly associated with hospitalization. And the final step is we are working towards developing a temporal model. I'm going to talk a little bit about the motivation for the temporal model and what do we see and the challenges that we are facing. and I'm going to show some results for the first 3 steps. All right. So first step is we did feature selection. We use multivariate feature selection as a part of feature importance score obtained from random forest. Some of the features that we identify as very highly predictive of hospitalization includes age, GFR, body weight, systolic diastolic blood pressure, heart rate, and lots of counts were very highly predictive of hospitalization according to a non-temporal model. Medication refill consult count, condition count, medication count, telephone consult count. We then use these features to represent our data and our labels where whether a patient has been hospitalized ever or whether has never been hospitalized.
What feature selection method?
So this one is in tandem with classification, a random forest feature score.
So you just based on the random forest feature score, and then you take the first top few variables.
Right. We did
the threshold. How do you set up the threshold?
How did we set up the threshold? So I iteratively reduce the least important features until the training set performance decreases. So recursive features elimination. Does that make sense?
So you just arbitrarily choose the threshold, or you did a cross validation threshold, like how many important features?
No, so I recursively remove least, I think in my case, least 5 features one at a time, and then do the whole experiments again, and again remove the least 5 feature importance and repeat it until the performance started decreasing, and then I stopped. So
how many original features data set?
So for the result that I'm showing here, I think there was just 23 features. I did not use all the conditions and medications. I didn't.
How many did you use?
In this case, I used 23 features, but in our data set, we do have, if we look at the medications and conditions individually, we do have 500, 600 features.
So you did like a pre-screening?
Yeah, because this is a pre-screening because our aim is to develop temporal model, and with that high feature space temporal model, I would say this is the first pass. If we don't get very exciting results, then I'll start including more of those nominal variables.
So did you take care of missing values?
Did you take what?
Missing values.
Not for this one. For the CKD prediction, the previous projects I did.
So for this data, you have a complete observation, no missing.
For the classification, yes.
No, for this prediction of the hospitalization.
I do have missing values.
Okay.
Did I take into account missing values?
Yeah.
I did take into account in the next step when I'm showing the unsupervised learning. I did take into account missing value.
Okay.
For the so we are using EM algorithm, and we incorporate the missing value in the data. We don't ignore. But for the classification, I did ignore the missing values. The records that were missing was dropped.
Okay, thank you.
All right. So then we used a simple supervised a random forest classification, and we find that the performance is not very exciting. It was in the range of 64-65 precision left measure. This gave us a direction that probably utilizing temporal information would enable us to improve our prediction performance. However, before going into temporal model, we also wanted to see if the features that the list of these features together in a multivariate manner, if they have some association with hospitalization. We wanted to do some pre-temporal model analysis to see if we obtain groups of patients who have direct association with risk of hospitalization. Okay, actually, before going into unsupervised learning, I wanted to show a little bit about what is the motivation for temporal modeling. So here I'm showing a patient story. This is one individual patient for whom we have GFR. We have the GFR values plotted over the period of time. Diastolic blood pressure values plotted over the period of time, systolic blood pressure, telephone consult count, heart rate, medication count. Now we see the red dots indicates the patient was not hospitalized during that visit, and the blue dots indicate that the patient was hospitalized. I'm calling this the patient story. Here we see that the GFR dropped. Seems like when the GFR dropped, the patient was hospitalized. Along with this, around the same time, the diastolic pressure remained almost the same. The systolic pressure dropped quite a lot. The number of telephone consult count increased from 0 to 4. That is a lot because on an average there were 5 telephone consult count at the higher end. Sorry. And then similarly, heart rate increased, and then medication class count also increased around that visit. So this is a neat story, right? Like GFR drops, diastolic, systolic blood pressure decreases, telephone consult count is increasing, heart rate increasing, medication count increasing, and hence boom hospitalizations happen. So if you were able to see this pattern again and again, we wanted to capture these kind of information in our temporal model to predict the risk of hospitalization. I'll show another patient story similarly, which followed similar direction of increase or decrease of value. That is, GFR dropped, hospitalization happened. So this blue point is the same point. It's just I'm showing the plots for different variables. Diastolic blood pressure increase, systolic blood pressure increase, medication counts increased a little bit, telephone consult count again increased a lot, and condition count increased, number of time refill consult count before the hospitalization increased, and the patient was hospitalized. This is awesome. However, the data is extremely heterogeneous, and this story wasn't captured. I just found 2 example patients. There are some patients who did follow this pattern, but majority of the patients did not follow this pattern. For example, I have a patient record. Their x-axis shows the GFR values and y-axis shows the time period. Again, the blue dot shows hospitalized event, and the red dot shows, I should have flipped the color. Red is more high risk, but here red is low risk. The blue are the hospitalized. As we can see here, that at this point the patient was hospitalized, but the GFR value increased. Similarly, at this point the patient was hospitalized, but the GFR value was pretty stable for some time, for almost a year. And similarly, for this patient, for example, there is a steep drop in GFR value, but this patient was never hospitalized. And if we see similar pattern for other variables, we do not see a trend where if GFR drops, if heart rate increases, if number of office visit records, number of telephone consult count increases, then hospitalization is happening. So what I'm trying to get at is there is an extreme amount of heterogeneity in the data, and a consistent pattern it does not indicate hospitalization. It seems like predicting CKD was much easier than predicting hospitalization, but probably that was the expected case. So the next step that we took was to see if change of values of all these variables together has some latent structure or has some clusters that can directly be associated with hospitalization. So I used a probability-based clustering algorithm, EM-based clustering. I'm just quickly going over very briefly what is EM clustering. It consists of 2 steps: expectation step, where we calculate the probability of each patient record to belong to a cluster, and the maximization step, where we, using the expectation step value, we calculate the parameters of the model. That is, we calculate the new parameters, including the mean of each cluster, the covariance matrix of each cluster, and the mixture coefficient of each. Just holistically, just a brief example. This is not from my data. This is just an example from a previous analysis. So let's say we have 3-dimensional data. That is, we have 3 values, and we want to identify these groups that seems to be similar to each other. We obtain this mixture of Gaussian distribution, and we plot them on 2-dimensional space. We can find these 3 clusters. These are pretty neat, tight, distinct clusters, and using 3 attribute values. That is, three columns in the data. This is what we were hoping, that we obtain some clusters that we can say, hey, look, the red clusters seem to have those value, the combination of those values which are more likely to be associated with hospitalization. However, we did obtain distinct clusters using our patient records. So here I'm showing 5 clusters obtained using EM, and the variables that I used for representing each patient was condition count, systolic blood pressure, diastolic blood pressure, or medication count. I did many other experiments using more number of features, but here I'm showing when the data set was represented using these 5 features. And these are means. So the black line represents the mean of one cluster. The blue line represents the mean of another cluster. Similarly, the red line is another cluster. We do see that at various dimensions, the values captured in different clusters are quite distinct from one another. Although now I'm realizing I should have shown the standard deviation bars here, but they were quite distinct from one another. So this is cool that we found clusters that were distinct and non-overlapping clusters. However, to our surprise, what we found is none of these clusters predominantly were related to hospitalization. Here I'm showing a summary statistics of the number of hospitalized. So the Y here, blue color, represents if a patient record was associated with hospitalization. That is, if a patient record was around the time when the patient was hospitalized. NH, the green, represents the patient was never hospitalized, and red represents the patient was hospitalized at a different time, but not during the time the record was collected. And we do see that all the 3 colors are pretty almost equally distributed, not equally distributed, but pretty well spread around all. The cluster was very small, so it's almost not visible. And hence, what we were hoping is if we get 1 cluster or 2 clusters which are higher with respect to never hospitalized patient, and some clusters which were more associated, more blue, more associated to hospitalized patient. We did not see that pattern, and this is just one example. I repeated it using other clustering methods and other feature vectors. However, now I'm trying to do some temporal clustering, that is using the temporal information of the patient over the period of time, and some methods like DTW, dynamic time warping, and other temporal models, and hopefully we'll have some patterns which enables us to identify risk of hospitalization. So as an ongoing work, we are working towards developing a temporal model. The plan is that we are hoping to use these clustering results as initial states and apply hidden Markov model kind of approach and be able to predict hospitalization of patients, or at least give a risk score for patients who are highly likely. And just as a disclosure, which Dina asked me to put. Thank you so much. Yeah.
So the hospitalization, obviously a big challenge you're finding. What I recall from prior presentations around the data set, the thing you're always going to have with hospitalization is what if the hospitalization is outside your data? Right. You can't capture everything. It will be interesting, of course, this starts to subset your different populations, but what you found with your first study is there are classes of, and in some of those, it wasn't necessarily that diagnoses were clustering together as they're synonyms for each other. Like your cardiac one, you had 4 different ways to say heart failure, which is a problem with the ICD coding and what we as physicians put in that complicates your process. But it would be, my general thought about CKD patients is they're not admitted because of their kidney disease, they're admitted because of their chronic condition. So it's how can you identify populations of patients based on your clustering in study 1 to see what factors is it that lead a heart patient to go on to hospitalization, primary COPD lung patient to go on to hospitalization, a primary diabetes patient to go on to hospitalization.
So let's subdivide the population based on comorbid topic condition. The heart patient topic could behave differently versus the lung patient topic.
Correct.
Okay. Yeah, that's a great idea. I was thinking about using the topic model hospitalization records topics that we obtained that was very different from the office records topic. Use as features like the conditions that were identified as high risk among hospitalization records to use as features. And if a patient has that condition, probably there is some association to hospitalization. But what you're suggesting is to even look at different sets of population.
Yeah, I mean,
like both ways. Yeah.
Yeah, I mean, one thing as an example to pull out is patients with heart failure typically have a low baseline blood pressure. So you're not going to find a change in blood pressure in their presentation because they don't have room to bounce around like other people. So a different feature may stand out as to what changes for them, probably a weight gain. common thing with heart failure is what leads to hospitalization.
what?
Where obviously a COPD patient or lung patient, you may have high blood pressures for them, and so changes in that blood pressure or escalation in their medications may mean something different.
So the baseline itself will be different for different populations. So yeah, thank you so much.
Just a quick comment. So related to the hospitalization, the fact that the patient, we don't capture all the things for all the patients. That's absolutely true. What we try to do though is limit this population to the Newcastle County to, make sure that we had as many patients coming here, but we are still missing, obviously, we're still missing some of
I mean, it's a good limitation, but the one patient story you showed where the GFR drops from 90 to 30, it could happen, and your nephrologist will tell you differently. But I find it hard to believe that patient wasn't hospitalized at that point, but perhaps they were wintering in Florida and we missed it.
See, I guess I have a question related to your selection, and it goes back to the question that Shanshan was asking. So you pre-selected a number of features.
And the features that I showed here was only not opening up the medications and conditions, just using the continuous variables. But then I do also use, so when we include conditions, we have whether a patient has this condition or not. We can also have a feature where a number of conditions the patient has. So the initial pass was to limit the variables. I just use the continuous variables. The summary. And then for the CKD, we opened up everything. We had 0, 1, whether a patient has this is taking this medication or not, whether the patient has this condition. Because for the hospitalization, our target is not to restrict to supervised and supervised learning, to build a temporal model. And as a first pass, if I'm letting my feature space explode, the model is just going to continue becoming complex without. If I do get a stable model which gives us some indication of good prediction, then including more features will be the next step.
Because did you mention the labs? Because I think there is a GFR, but there are also many other labs like sodium and all.
So I am taking into consideration few labs. I think 3 or 4 labs currently, but the labs are so high misdata that because only few patients are ordered some labs at a particular type 1. And I figured out a way to collapse the lab, like if a patient had some lab tests within last 2 months, I'm using that as information and making the lab test records a little more less sparse. But yeah, in this pass, I haven't shown the lab test, but I am including lab tests, and we will discuss that more.
Okay, thank you very much.
Yeah.
Sorry. So I saw that one of the body
During the hospitalization?
Yes.
So many animations.
It's okay. I just have one question. How did you deal with missing values in this feature exactly? Because I'm working on a model, and I know that sometimes we replace the missing values with the mean. Sometimes we can just ignore them. But what do you usually do?
So for the supervised learning approach, I dropped the records that were related to missing. Because we have a large data set, we can afford to do that. However, for clustering, for the expectation maximization, I was calculating the model expectation of maximization by ignoring that particular value, but using the rest of the record. So I incorporated the missing data as an information for the clustering, but for supervise, I ignored the record. I dropped the record.
And when you have...
But imputation is also another way we can go, but imputation needs more like instead of just imputing with means or selecting a population and calculating the mean, it's better to maybe consult with a domain expert to see if that imputed value. Oftentimes, imputation can create bias in the data. So if someone is imputing, I think more serious considerations are needed. But yeah, please go ahead and ask.
that's it. Because, like when you have a high number of missing values, you can ignore the missing values.
Yeah.
But
Absolutely.
for the lab test,
Right.
But I think one of the ways to do that also is consider the lab test, whether it's done or not, because that can be an indication also of what the physicians have ordered. Now, if a lab test in our electronic health record, if a lab test is done, that's already, an information about the patient. And if a lab test is not done, that's also information about the patient. So if you have a lot of missing value related to a lab test, then just transform the variable and say done or not done.
Like 0, 1.
Because that really gives you an indication about the patient.
And it can also be clinically useful as we were thinking about this, is like having a measure of how long it's been since they've been seen in office may also end up being a predictor, and that's something you could act on.
Right.
If you know, this patient hasn't been back to see us in 6 months, we've got to give them a call or they're going to be hospitalized in the next 3 months. That's something an office can act on.
So use that information as a parameter of the model, like how many times a patient has come for office visit versus
For the time since they've been last seen.
okay.
Time since last.
Yeah. And of course, the other thing is, of all the patient samples they have, look at the admitted diagnosis, primary, secondary. As he brought up, if this is usually a secondary diagnosis, that you're not going to be able to find something rock solid or something. Right.
So I think we are not really looking at the diagnosis. I mean, hospitalization, basically yes or no, is the outcome here. We are not really looking at the diagnosis of hospitalizations, in the hospitalization model as the outcome. It's really yes or no. I mean,
We just want to provide a risk, whether
Right.
looking at the patient information, whether the patient has high likelihood of hospitalization. Yes or no, or just
But
some
as
risk.
I said, I think longitudinal is extremely important. I'm not a clinician. Said it on some of the discussions about even monitoring patients, in-house. Here's a lab value, or here's a vitals value. Well, it's not just the value of that; it's how's that. That becomes extremely important. So if you just look at data points, you don't see that trend. That trend, is what starts to lead. I've heard them say, "Hey, I'd love to see a chart on how this is doing over the last few visits. Where is it going?" Because you can have one data point that's going to pop up or down because particular thing that has to be going on during that day.
But the challenge that I'm facing with this is if there is a consistent trend that is a signature, a motif that is indicating hospitalization or higher risk, it doesn't seem like there is this consistent trend. At least I haven't found it so far. But that is my pursuit, to be able to find if there is this trend that indicates that when the GFR goes in this direction, when the heart rate goes in that direction, if this lab is taken and that lab is taken, it leads to the multivariate trend.
Yeah, that's one of the things. I'm not a clinician. Hearing about, man, if I could just, over the last 2 months or 4 months, look at these things, that gives me more information. You can tell me whether that's good or not.
No, this is exactly the goal of basically dataset, because we have so many longitudinal records.
Right.
So there are so many data points. That's what we want. That's what Momita is really working on. Is a trend.
But the structure of the current data analysis is fine. So I'm not sure how we take the tools that we have and start to put in things like time since the last visit, or the difference between this value and one of the three visits ago, or how do we bring in the longitudinal information so we can see a progressive change?
I mean, time since the last visit, we have that.
Thank you.
That's what we have. Okay, any other questions? Right, thank you very much.